Hey everyone, welcome back. So, calculus is built on two main ideas. The first is rate of change, which tells us how quickly something is changing. And the second is accumulation, which tells us the total amount or how much of something has built up over time. So, in the first half of the course, we focus on rate of change. We start with limits, which help us understand what a function is approaching, even if it's not exactly defined at that specific point. So, let's go back to Algebra 1 and our slope formula, which is just y2 minus y1 over x2 minus x1. In calculus terms, this is just the slope of the secant line. So remember, I want to make it really clear here that rate of change basically just has to do with slope. So basically what we can do in calculus is we can take those 2 points given by the secant line and we can move them infinitely close to each other using limits, and then we get the tangent line, which gives us the instantaneous rate of change at that specific point on the curve or at that specific point in time. So again, up until now, thinking back to your math career, in algebra, you're doing the average rate of change or the average slope, but in calculus, we start to learn how to get the instantaneous rate of change at a specific point in time. This is where derivatives coming in. So basically, by using limits, we can calculate the derivative, which gives us, again, the exact rate of change at a specific time. So derivatives are useful because they describe how things are changing. So this could be speed, it could be growth, it could be profit. So we learn various rules for calculating derivatives quickly, such as the power rule. And then we basically use derivatives to understand the behavior of functions. So we want to see when they're increasing, when they're decreasing, when they reach their max or min values, and then basically just how their graphs behave. So some real world applications for derivatives could be solving problems that have to do with motion, right? Position, velocity, and acceleration, optimization, meaning finding maxes or mins, or even related rates. So moving on to the second half of the course, we shift to the concept of accumulation, which again is about figuring out how much of something has built up over time. So to calculate the area under the curve, we start by using Riemann sums. So initially we approximate the area by dividing the area under the curve into rectangles. So again, we're going back to much earlier math formulas, right? Because we learn how to find the area of a rectangle usually in geometry, which is just length times width. However, we can tie in calculus and we can basically make this approximation of the area under the curve more accurate by increasing the number of rectangles. So as the number of rectangles approaches infinity, the sum becomes an exact value, and that's what we call the definite integral. This leads us to the fundamental theorem of calculus, or FTC, which basically connects those two parts. So it connects the concepts of derivatives and integrals and basically tells us that these are inverse processes. So while derivatives measure change, integrals measure accumulation. With integrals, we can solve a variety of problems. For example, we could find the total distance, the area between two curves, and the volume of solids. We can also use integrals to solve differential equation by separating variables and also visualizing solutions using slope fields. So to tie this all together, once again, derivatives measure change, integrals measure accumulation, and the FTC basically connects these two concepts and shows us how they're inverses of one another. All right, hopefully that helps, and I'll see you in the next one.